Predicting Success of International Players in the NBA by Ashley, Tolu, and Dennis. Drafting international superstars can be the difference between losing and winning in the NBA. Just last year, the San Antonio Spurs won the NBA championship with 7 international players on their team, but most teams haven't had half the success. And making drafting mistakes can be costly, as the Detroit Pistons found out in 2003 when they drafted Darko Milicic. On today's agenda, first we're going to introduce our project goal, then discuss some of our data collection, analysis, and make predictions about current NBA prospects. So our project goal was to build a model to predict adjusted plus-minus of international players in the NBA based on their prior experience in international leagues, and use that model on current international prospects. Unfortunately, the largest part of our project was data collection. Simply collecting all the data from international leagues proved to be very difficult and took about 3.5 weeks. Our data consisted of 175 players, 63 attributes, and 1 international season's worth of data from the year directly prior to their joining the NBA. We did not include rookies, guys who reached their prime prior to 2000, players with less than 500 minutes, or players who only played overseas during the 2011 lockout. Here are our attributes. We included demographic information, draft information, team information, per game stats, and per 40-minute stats. Per 40-minute stats were per game stats scaled as if the player played 40 minutes per game on average. Here's our dependent variable, adjusted plus-minus. It's a measure of an NBA player's peak performance in terms of how much they contribute to their team's chance of winning. The mean of our sample data, negative 1.02, was close to the population mean of negative 0.9. It's heavily right skewed, and only 38 players out of 175 had a positive APM. A major problem we encountered is that many players played on 2 or more teams during their prior year. Thus we created a weighted average of their statistics. This weighted average set outperformed data sets featuring only data from their most played team. Moving on to the analysis, we tried regression and classification. In order to predict adjusted plus-minus, we tried linear and k-nearest neighbors regression, as well as random forest regression trees. Just predicting the mean APM yielded a mean squared error of 5.48, and unfortunately, none of our models were significantly better. Our best model, a 38 k-nearest neighbor model using triangular kernels and 7 features, had an MSE of 4.9. The small sample size, large number of meaningless attributes, and negative skew of APM made the data too noisy for us to predict with these methods. We were about to give up. But CMU students never give up. So our next approach was classification. We binarized adjusted plus-minus into good players and not so good players. We ran SVM, random forest, naive Bayes, logistic regression, and KNN. We tried different kernels, number of variables at each split, different numbers of K, etc. KNN performed terribly, as did SVM and random forest. Whereas KNN picked random players, SVM and random forest only picked well-known superstars, thus providing absolutely no value to clients who would use our model. But naive Bayes and logistic regression worked well. In purple, you see a logistic regression model using features selected through backward stepwise regression. This model only used per 40-minute statistics. In green, you see a naive Bayes model using the same feature set. The arrow indicates the threshold value we decided to use. A major concern for us was balancing precision and recall. Drafting a bad player can cost millions of dollars, making precision very important. However, a model that only predicts obvious superstars is worthless. We want a model that can spot diamonds in the rough, and thus recall is also important. Thus, we settled on trying to maximize precision while keeping recall high enough to be useful. We settled on a naive Bayes and logistic regression model which equally had a precision rate of 55.56% and a recall of 39.47%. We then tried to predict current international prospects using both models. Out of 22 players, naive Bayes predicted that 6 would have positive APMs, while logistic regression predicted that only 2 players would have positive APMs. Our models agree on only one guy, Nikola Jokic. Our study had many limitations. We were missing data from 115 players. Our model is better than random, but it's still pretty risky. Some interesting features were entirely absent, like English language ability. In conclusion, predicting APM proved to be a difficult task. Per 40-minute statistics seemed to work better, and feature-selected naive Bayes and logistic regression performed best. In the future, we'd like to build a multi-class model, an anomaly detection model, and a Bayesian net. Thank you very much.